We present a computational tool for designing compliant mechanisms that, instead of rigid articulation, obtain their function by virtue of elastic deformation. Our method takes as input a conventional mechanism and replaces rigidly articulated joints with flexures, thin blades of elastic material whose shapes are automatically computed in order to optimize the performance of the compliant mechanism. There are several design objectives that need to be taken into account. First, we would like the compliant mechanism to closely track the motion of functionally important points on the input mechanism. The example here shows the motion of an end effector before and after optimizing the mechanism with respect to the tracking objective. Unless explicitly prevented, collisions may arise during optimization as flexures adapt in order to better approximate the desired motion. In order to guarantee proper function of the compliant mechanism, we introduce additional objective terms that strongly penalize intersections. In this way, we obtain mechanisms that can, in principle, move without collisions while tracking the target motion. However, this is not sufficient for proper functioning, as deformations in the flexures can induce large internal stresses, which in turn lead to material fracture. In order to stay at a safe distance from material failure, we minimize the peak stresses in the mechanisms over the entire motion cycle. Actuating a compliant mechanism requires a finite amount of work in order to overcome the elastic forces due to deforming flexures. We therefore also optimize the mechanism such as to minimize the maximum torque needed in order to drive the mechanism. Here we show a more complex example of a Janssen leg, in which we replaced 9 conventional revolute joints with compliant flexures. As can be seen here, naively introducing flexures without optimizing their parameters leads to poor results in terms of trajectory tracking and elastic energy. Even for this complex example, our method is able to closely approximate the original trajectory while avoiding collisions, minimizing torque, and preventing material failure. Our tool is not limited to planar assemblies and is well suited for converting spatial mechanisms too. In this example, we show a compliant wing that forms an integral part of a dragon model. In order to ensure robustness in both planar and spatial cases, our method simultaneously accounts for internal stress with respect to stretching and compression, bending, and twisting. Our method can also maximize stiffness in lateral directions. As shown in this example, our method can also maximize stiffness for directions in which compliance is not desired. Here, the optimized steering mechanism of the car is stiff enough in the vertical direction to support the weight of the car, yet sufficiently flexible for in-plane motion to warrant safe navigation. For conventional mechanisms, scale-independent fabrication tolerances lead to increased play relative to the assembly size, decreasing accuracy. Furthermore, when using 3D printing, residual support material increases friction in the joints. As shown in this example, these drawbacks can amplify in unfortunate ways, leading to unforeseen deformations in the structure and even failure. We show the ability of our method to scale to miniature designs, found, for example, in small-scale animatronics. By explicitly modeling compliance, we can predict and leverage the deformation of the structure and maintain proper functioning with good precision. We demonstrate our tool by designing and fabricating an exoskeleton hand featuring 5 compliant fingers with 18 flexures each. Since the flexures pull the fingers back to their undeformed state, we are able to actuate the entire hand with only 5 individual strings. Thank you.